Chapter 1. Doing Arithmetic. Section 1. Data. First, let's start SPROC and click the new icon. Now you will see a grid-style interface like this. We write SPL code in this Excel-like grid, but of course this is not Excel. Most programming languages only support text-style code. Generally, the code is executed from front to back if no special code is to change the order. SPL is slightly different. SPL code is written in a grid called a cell set where all cells can be filled with codes and executed from front to back. Specifically, SPL code is executed cell by cell. Each cell is executed from left to right in each row, and then the cell of the next row is executed. Though the two coding methods are not essentially different, we will see later that the grid-style coding is more friendly for non-professionals. Most programming books have been accustomed to starting with a simple "Hello, World" example program, a legacy of early command line era and a third wheel for contemporary GUI operating systems. And we just admit it. A computer program should be able to do what a calculator can do. Let's see how SPROC does the arithmetic by coding in the cell. The equal sign preceding the code in each cell is compulsory, just hold your Y for a while. The parentheses must be in English format, error will be reported if they are in the Chinese format. Now press Ctrl F9 to execute the program and the background of the code area will turn pale yellow. Click a cell and you can view its value in the right-hand section. Before the execution, the background of the code area is white and a click of a cell containing code will not display a value on the right-hand section. Unlike Excel, SPROC does not compute automatically. Generally, computer programs do not automatically execute an action until a special execute operation tells them to do that. Now let's look at these computed results. Like an Excel formula, an SPROC formula has multiplication represented by an asterisk, division by a slash, and performs computation in the order of multiplication and division first and then addition and subtraction. Like an Excel formula, each layer in an SPROC formula is represented by parentheses rather than brackets or braces. An error will be reported if the wrong symbol is used. Also like an Excel formula, an SPROC formula can compute positive and negative numbers, decimals and integers. Take a closer look at the computed results and you will find that the results of A1, B1 and A2 are integers written without decimal points, while the results of B2 and B4 are integers written with decimal points, as shown by 3.0. Why are there decimal points in the latter but there are not in the former? Because computers identify numbers with decimal points and integers as different types of numbers. The former is called floating point numbers and the latter integers. When performing arithmetic operations, we usually don't care whether the numbers are floating point numbers or integers, as long as the result is what it is. However, when programming with a computer, the first thing we need to do is to determine the type of numbers to be calculated because different types of numbers are stored and calculated in different ways. If we get the data type wrong, the result may be wrong. Therefore, identifying the data type is a foremost and basic task. Is it necessary to distinguish integers from floating point numbers? Since we can treat integers as floating point numbers where the fractional part is 0, then why don't we just use floating point numbers? It is mathematically okay. But there are technical problems for computers to perform the related operations. Since it is much simpler to store and compute integers than process floating point numbers, processing integers of floating point format is as inefficient as processing real floating point numbers. So that is not a wise choice to make, particularly when the computation mainly involves integers. As computers cannot know the difference, it is the programmer's job to make the right decision. Most programming languages differentiate integer from floating point number but allow them to appear in the same expression. To compute the expression, we will convert the integer to the floating point number. An integer can always be converted to a floating point number, but not necessarily vice versa. The result of a division operation could be a floating point number, so SPL specifies that the quotient should always be of the floating point format to ensure that data type of the result is explicit and definite. SPL also defines a type of division operations that return integers. This type of division is represented by the backslash. If you are interested, enter =6\3 and =5\3 to see what will you get. Let's move on to view the computed result of A6. It is 0. What happened? A large number requires a larger space to be stored. The computer's memory, however, is limited. The machine cannot represent an infinitely large number. We thus put a restriction on the size of data. Most contemporary programming languages have two representations for integers, 32-bit binary integers and 64-bit binary integers. This means the largest number computers can represent are 2 to the power of 32 or 2 to the power of 64. The actual size is half smaller because the other bit is used to represent the negative number. Error will happen once the computed result exceeds the limit. The largest integer SPL can handle is 64 bits. Since the number 65536 to the power of 4 exceeds the limit, an error happens. Unfortunately, almost all programming languages, including SPL, do not report the error but let it be. Programmers can only rely on themselves to avoid the mistake. Why are the 32-bit integers and 64-bit integers selected? Two foremost reasons are usability and efficiency. 32-bit integers are sufficient for most operations, while 64-bit integers occupy too much space and are less computationally efficient, which makes them necessary only in certain few occasions. The 16-bit integers are often inadequate, and inventing another type of integers makes the list a little crowded. Actually, 16-bit integers and even 8-bit integers were once used on early computers. Interestingly, the number of bits of all these types of integers are 2 to the power of n. There have never been such bits as 18 or 25. SPL calls 32-bit number integers and 64-bit numbers long integers, just like the other contemporary programming languages. Early programming languages may have different conventions. The fact is that both 2 to the power of 31 and 2 to the power of 63 are extraordinarily large numbers. Since it is rare that such a large number is used, it is not that important to dig deeper. The computed result in A7 is also not what we expect. And why? Similar to integers, storage space is limited for floating point numbers. On the other hand, floating point numbers are finite and can only be represented by a limited precision of about 18 significant figures. Extra figures should be discarded. Thus error in A7 happens. In addition, this is also important. We know that contemporary computers use binary numbers to perform calculations. The binary counterpart of a decimal integer can retain the original precision. But a decimal finite decimal, such as 0.1, probably becomes a recurring decimal which cannot be precisely represented by computers after it is converted to a binary number. You can think about the principle behind it yourself. Deviation can be accumulated to lead to unexpected error when the imprecise number undergoes a series of operations. In contrast, integers are always precise after a series of operations. Therefore, integers are the first choice on all possible occasions. Let's look at A8. Unlike A6, it records 65,536 as 65,536.0, which tells the computer that this is a floating point number instead of an integer. SPL will convert a number to floating point format, which has a far greater range than integer, for computations to get the correct result instead of an overlimit number. But what does 1.844674073709552E19 mean? This is the scientific notation conventionally used by all programming languages. Here it represents the number 1.844674073709552 times 10 to the power of 19. In a cell code, the number 1.23 * 10 to the power of -20 can also be represented by 1.23e-20. Apart from integers, long integers, and floating point numbers, other data types in SPL include huge numbers, which represent numbers of any length and precision but process slower, strings and date, time and date time. All will appear in the following sections. Understanding the basic data types is the foremost thing to learn a programming language. Section 2. Variables and statements. We know that the area of a circle, S, is equal to pi times the radius of the circle squared. Now we write a piece of code to calculate the area of a circle with the specified radius. Here we take 3.14 as the value of pi. Execute the code and view A2's value, which is the area of a circle whose radius is 5. To calculate the area of another circle whose radius is 7.8, we just need to change A1 to the specific value and then execute the code. Now the value in A2 is the current circle's area. Let's examine the expression in A2. It contains a cell name. It references A1's value at computation and uses the new value whenever there is a change to A1. That is, this expression references a value through the name of cell containing it. It is easy to understand for one who is familiar with Excel. Programming languages call named data the variable, like A1 and A2. We can write equals A2 * 4 in A3 to calculate the area of a ball with A1 being the radius. A3 is also a variable. All cells in the cell set are variables. Then we can reference a variable in a computing expression. A recomputation of the expression with a new variable value will get a new result. So coding only once for computing multiple expressions of same pattern. It is convenient and error immune. Computers are indeed good at doing the repetitive work. Excel also has this merit. Is the variable thus named because it is variable? That's it. A variable can get a new value in a program. Let's see this piece of code. A2 and A4 have same expressions, but they get different results after execution. A3 modifies the value of A1 to 7.8 when executed. A4 then takes the new value for A1 to do the computation. This is different from Excel. The spreadsheet tool cannot modify a cell value by writing a formula in another cell. Instead of the equals sign, the code in A3 is headed by the greater than sign. In SPL, a cell whose content begins with equals sign is called a calculation cell, and one whose content starts with greater than sign is called an executable cell. A calculation cell calculates the expression after the equals sign and puts result into the current cell. An executable cell executes the action after the greater than sign but will not put any value into the current cell. In the above code, the value in A3 is still null after it is executed. Cell A1 in the above piece of code, with neither the equals sign nor the greater than sign, is called a constant cell in SPL. It is used to define a constant. Many programming languages have the concept of constant variable, which can be understood as the named constant. The constant variable value cannot be changed at running time of the program once it is set. The constant variable can also be regarded as a variable that can only got assigned once. The introduction of constant variable aims to avoid changing the variable value that should be kept unchanged when code is wrongly written. SPL does not have the strict concept of constant variable. The value of constant cell A1 in the above code can be modified by the execution of an executable cell. Generally, a program written with a programming language is in text format, sentence by sentence. The sentence-wise format is more apparent in programs written in earlier programming languages. Each sentence describes an action to be carried out. Such a sentence is called program statement. A piece of program is made up of a set of program statements. SPL does not feature this sentence-wise coding format. In a SPL program, code in a cell can be treated as a statement. Both a calculation cell and an executable cell are statements. In most programming languages, programmers need to name variables. SPL supports user-defined names too, as shown in the program. Here letter R, rather than A1, is used to name the variable. Results are the same. Pay attention to the right bottom section of the interface, where the value of the variable, R, will be displayed. The advantage of a meaningful user-defined variable name is unforgettable and not easy to confuse, such as the R used in the above program. It is the same R as the one in the formula for area of a circle. Sometimes when the variable is used for storing an intermediate result, you can give it a not so meaningful name. But there is a probability that it is a namesake. In SPL, you can name a variable after the cell name. This is one of the small conveniences that the grid-style coding format has, but that the text coding format does not have. There are two variables, A and B, and we need to exchange their values. The general program is like this. The newly defined variable C can be renamed after the cell name. Like in Excel, when the cell name is used as the variable name in SPL and when a row or column is inserted or deleted, the cell name referenced in an expression will be automatically adjusted to get the right result. SPL's another Excel-like feature is to use the $sign to fix a cell to the specific row and column when a row or a column is inserted or deleted. SPROC also offers some commands and their shortcuts on the Edit menu. When you are familiar with the SPL features, you will find that its grid-style coding format is far more convenient than the text coding format. By the way, SPL is a case-sensitive programming language. The lowercase r and the uppercase r generate different effects. The cell name used as a variable name should be the uppercase. The uppercase A1 represents a cell variable while lowercase a1 is only an ordinary variable. Some programming languages are case-insensitive, where the lowercase r and the uppercase r produce same effects. A sign that can be used as a variable name is usually made up of letters and numbers and must not begin with a number. It can contain the underline. The underlined sign is generally treated as a letter and can be placed at the beginning. SPL also allows using the Chinese character in a variable name. Identifiers are the jargon for the signs that can be included in the variable name. Another question, does a variable have a data type? There are two types of programming languages. One is the strong-typed languages, such as Java and C++. They require that a variable's data type be declared before it is used. If variable x is declared as the integer type, it cannot be used to store a floating point number. If it is assigned a floating point number, it will be automatically converted into an integer, and lost information during the process. The other is the weak-typed languages, such as SPL. In SPL, users do not need to declare the data type for a variable. The appropriate type will be naturally generated during the computation. Does it show that the weak-typed languages are more convenient to use? It does in terms of usage convenience. But as a strong-typed language declares the data type of a variable in advance, the computer knows how to store the variable before execution and thus gets a better performance. A weak-typed language decides the storage method after the result is obtained, which makes computing performance poorer. There is no perfect thing of the kind. Take the formula for the area of a circle as an example. This formula is in essence an equation. It tells that the area of a circle S is equivalent to pi times r squared. In fact, the equation will still hold if they switch positions. Now we write the formula in SPL statement to calculate the area of a circle, greater than sign S equals 3.14 *r**r. Is it an equation too? No. In a programming language, a statement that sets the value of a variable is called the assignment statement. It represents an action, rather than being a mathematic equation. It should not be written as greater than sign 3.14 **r**r equals S. This statement makes no sense. The computer will report an error for it. An assignment statement calculates the expression on the right of the sign equals and assign the result to the variable on the left the sign equals. The calculation of the expression is irrelevant with the variable. The assignment will only begin after the calculation is finished. This way an equation that is mathematically impossible will become a common assignment statement like greater than sign x equals x plus 1, which denotes that the current x value plus 1 and the result will be assigned to x. Suppose the value of x is 3, then its value will become 4 after execution. You will basically understand the concept of variable if you can figure out what x equals x plus 1 means. This can be counted as the first small barrier in the course of learning program design and a concept that Excel does not have. Look at this piece of code. Try to change the initial values of both a and b multiple times and execute the program to see the final values of both variables. You can first make a guess and then try to prove your conclusion using the variable assignment principle. Early computers have small memories. One fewer variable means less memory usage, and programmers invented the crazy code to achieve this goal. Section 3. Functions. As we have said, data has types. A division operation may get a result of floating point number. If we need to get an integer, by rounding about the result, for instance, what should we do? It seems that we haven't introduced a method for doing this. Even if the result is an integer, like 6/3, it will be represented by a floating point number, 3.0. How will it be converted into an integer that can be identified by the computer? We need int function to get this done. Int x calculates the integer part of x. For example, int 3.0 equals 3, int 3.1 equals 3, int minus 3.0 equals minus 3 and int minus 3.1 equals minus 3. Here, the equals sign represents a mathematical equation rather than an assignment statement. Actually, the concept of function is introduced as early as in a high school mathematics textbook. For the time being, we can consider that the function concept in the programming language is the same as that in the mathematics. Both have the independent variable, which is called parameter in programming languages, and dependent variable, which is called return value in programming language. In the equation y equals f(x), x is the parameter and y is the return value, or we can say f(x) returns y, int x takes number x as the parameter and returns the integer part of x. It is called integer function. By the way, int x returns a 32-bit integer. The long x function is used to convert a number such as an integer, a floating point number, or a long integer to a long integer. There is also the float x function for converting a number to a floating point number. Usually, a practical program written in a specific language uses many ready-made functions that the language predefines. These ready-made functions are also called library functions, like they are stored in and retrieved from a library of functions. Generally, a skilled programmer needs to be familiar with hundreds of frequently used library functions. It is important and necessary to learn to use the library functions if you want to master a programming language. The significance of library functions lies in the reusability. The ready-made code for a specific operation that is packaged into a library function is convenient to use anywhere, anytime, while a rewriting is troublesome and error-prone. A function does not necessarily have parameters. SPL function, for instance, returns pi only. To calculate the area of a circle, we use the code greater than sign s equals pi asterisk r asterisk r. A function may not have a return value, like output x function. Execute the code and we can view hello world in the right bottom section on the interface. Output x function outputs the value of x to the output window on the right bottom section, so it will not return a value. A function that does not return a value executes an action instead. It is more like a statement. The word function also has the meaning of purpose or activity. This shows that the value return is the purpose or the target activity we want to achieve. For programmers, value returning is not the only significance of functions, they use them to do anything that can be done. In this sense, we sometimes call the use of a function calling it like it is called up to perform a specific task. Like functions in mathematics, functions in programming languages may have more than one parameter. Max x y, for instance, returns the larger one of x and y. Some functions have a fixed number of parameters. The power function power a x that returns a to the power of x always have two parameters. Max function, however, can have more parameters. Both max 1, 2, and max 3, 4, 5 are allowed. The parameters of a SPL function can have default values. Parameter n in pi function takes 1 as its default. Pi n means n times pi, but in most cases the function returns 1 pi. So pi means pi 1. It is important to know the parameter default values, otherwise you may not understand the code written by others. Not all programming languages support parameter default value. All features introduced as yet are not beyond Excel.